You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Sparsity, in the context of machine learning, refers to the idea that only a fraction of a model's parameters are active during the processing of any single input. In dense models, every parameter contributes to every calculation, creating a uniform workload regardless of the complexity of the input. Sparse models take a different path. Instead of engaging all parameters every time, they selectively activate only a subset that is most relevant to the current input. This selective activation means that models can be built with far more total parameters than could ever be used efficiently in a dense system, yet still operate at manageable computational costs per query. The idea mirrors human reasoning. When solving a math problem, you do not draw on every skill you've ever learned. Instead, you activate only the subset of knowledge relevant to the task at hand. Sparsity enables machines to do the same, making them more efficient and scalable. The motivation for sparsity becomes clearer when we consider the tension between scale and compute. As models grow larger, their capacity to store patterns and associations improves, often leading to better performance across diverse tasks. However, dense scaling means that inference costs rise linearly with model size, creating bottlenecks in deployment. Sparsity solves this by decoupling total model capacity from per-input compute cost. A sparse model can contain trillions of parameters, but for a given input, only a small percentage are used. This allows organizations to train models with enormous representational capacity while still serving queries quickly and affordably. In practice, sparsity provides a way to scale intelligence without drowning in compute demands, enabling researchers to push the frontier of model size without breaking infrastructure budgets. A prominent implementation of sparsity is the mixture of experts architecture. In these systems, the model is divided into multiple experts, each a smaller subnetwork trained to handle particular kinds of inputs. For example, one expert might specialize in understanding numerical data, while another focuses on narrative text. A routing mechanism decides which experts are activated for each input, meaning that only a fraction of the full network is used per inference. This approach allows models to scale far beyond what dense architectures can achieve, since capacity grows with the number of experts, but compute per input remains bounded by the number of experts actually consulted. The analogy is that of a medical clinic. While the clinic may have dozens of specialists, any given patient will only see one or two, making the system both scalable and efficient. Routing is the mechanism that determines which experts are engaged for a given input, and it is central to the functioning of mixture of experts models. Typically, a gating network computes scores that indicate how relevant each expert is to the input. The top-scoring experts are selected, and only their parameters are activated for processing. This dynamic routing ensures that computation is concentrated where it matters most, rather than spread thinly across the entire model. The challenge lies in designing routing strategies that are both efficient and fair, ensuring that all experts are used over time rather than allowing a small number to dominate. Effective routing transforms sparsity from a theoretical concept into a practical tool, enabling massive capacity with manageable costs. The capacity versus compute distinction is what makes mixture of experts particularly appealing. Dense models tie these two factors together. Doubling the capacity means doubling the inference cost. Mixture of experts breaks this linkage, allowing capacity to grow faster than compute cost. A model might contain hundreds of experts, representing trillions of parameters, but only 2 or 3 experts may be used per input. This creates a system that has enormous storage of patterns and associations, but requires only a small, predictable amount of compute per inference. For organizations, this means scaling without exponential cost growth, a critical advantage as AI models become central to products and services worldwide. The benefits of sparsity go beyond efficiency. Sparse models open the door to forms of specialization that dense models struggle to achieve. Because experts can focus on particular types of inputs, they may develop unique strengths. One expert might excel in legal reasoning, another in creative writing, and another in technical explanation. This division of labor makes the overall model more versatile, able to handle a wide range of tasks with high quality. At the same time, sparsity encourages interpretability. By observing which experts are activated for different inputs, researchers gain insight into how the model organizes knowledge internally. Sparse architectures thus combine efficiency, scalability, and a degree of transparency that is rare in large-scale AI systems. The idea of conditional computation and sparse activation is not new. Early neural networks experimented with activating only subsets of nodes or pathways, inspired by biological brains where not all neurons fire simultaneously. The concept of mixture of experts itself dates back decades, with early research exploring ways to divide learning tasks among multiple specialized submodels. What has changed is scale and hardware. Advances in distributed computing, optimization algorithms, and training strategies have made it possible to implement sparsity in models with billions of parameters, turning what was once a theoretical curiosity into a practical frontier of AI research. This historical continuity reminds us that many innovations in AI are rediscoveries of older ideas, refined and made feasible by modern technology. Modern adoption of mixture of experts has accelerated as organizations search for ways to scale beyond the constraints of dense architectures. Several frontier models now incorporate sparse techniques, activating only parts of their networks per query while maintaining massive total parameter counts. This has enabled breakthroughs in performance without unsustainable growth in inference costs. Sparse methods have proven particularly valuable in large language models, where the diversity of inputs benefits from expert specialization. Adoption has been driven both by necessity, the impracticality of scaling dense models indefinitely, and by opportunity, as sparse designs have demonstrated superior efficiency and competitive benchmark results. Training mixture of experts models, however, introduces significant challenges. One common issue is expert collapse, where only a few experts are consistently selected by the routing mechanism, leaving others underutilized. This undermines the benefits of sparsity, as the model fails to distribute learning evenly. Balancing expert utilization requires careful design of loss functions, regularization strategies, and routing algorithms. Another challenge is ensuring stability during training, since sparse activation can create uneven gradients and optimization difficulties. These challenges highlight that while sparsity is powerful, it is also complex, requiring new techniques and innovations to be harnessed effectively. Load balancing across experts is a related concern. For sparsity to deliver its full benefits, all experts must be trained and used effectively. If certain experts dominate while others remain idle, the system wastes potential capacity and may overfit to narrow patterns. To address this, training strategies often include penalties or incentives that encourage even expert usage. Techniques such as auxiliary losses or random routing injections help ensure diversity in expert activation. Proper load balancing not only improves efficiency but also enhances robustness, as the model avoids over-reliance on a small subset of experts. This balancing act is a critical part of making mixture of experts work in practice. An intriguing potential of mixture of experts is interpretability. Because different experts can specialize, researchers can analyze their outputs to gain insight into how the model organizes tasks internally. For example, one expert may consistently activate on mathematical inputs, while another responds to narrative prompts. This functional specialization resembles the way different regions of the human brain handle distinct cognitive tasks. By studying which experts are engaged, we can begin to map the hidden structure of knowledge within the model, offering windows into understanding what has often been a black box system. While still early in research, this interpretability potential adds an additional layer of value to sparse architectures. Fault tolerance is another benefit of modular expert design. If one expert fails or underperforms, the system can often route around it, relying on other experts to handle similar tasks. This modularity provides resilience that dense models lack, since dense systems depend on all parameters being active and reliable for every inference. In sparse architectures, redundancy and specialization can combine to create a form of graceful degradation, where failures do not cripple the system entirely. This makes mixture of experts particularly attractive for deployment in critical systems, where reliability and fault tolerance are paramount. Comparing sparse mixture of experts models with dense models highlights their distinctive strengths and trade-offs. Dense models are simpler to train and deploy, since all parameters are always active, eliminating the need for routing. They also avoid the pitfalls of expert collapse or uneven load balancing. However, dense models face scaling limitations. As parameter counts increase, inference costs rise proportionally. Mixture of experts models invert this trade-off. They introduce complexity in training and routing, but allow capacity to grow faster than inference cost. The choice between dense and sparse designs is therefore a matter of priorities: simplicity and uniformity versus efficiency and scalability. Performance on benchmarks has validated the promise of mixture of experts. Sparse models have achieved results comparable to or even better than dense models of similar compute budgets, demonstrating that capacity can be expanded without proportional cost. Benchmarks across language, vision, and multimodal tasks have shown that expert specialization can improve accuracy while maintaining efficiency. These results underscore that sparsity is not merely a theoretical improvement, but a practical advantage. As benchmarks increasingly incorporate efficiency metrics alongside accuracy, mixture of expert systems often come out ahead, offering both strong performance and sustainable compute usage. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. The scalability advantages of sparse models are profound. Dense models grow in both capacity and compute simultaneously. Every time you double the number of parameters, you double the work required at inference. Sparse models break this linear tie by activating only a fraction of the total parameters for each input. This means you can build a system with trillions of parameters while still keeping the per-inference cost comparable to a smaller dense model. In practice, this allows researchers to scale model capacity far beyond what was once considered feasible, storing more patterns, rules, and associations without making every query prohibitively expensive. Think of it like a massive library. Though millions of books are on the shelves, you do not need to consult all of them to answer one question. Instead, a librarian directs you to the 2 or 3 most relevant books, giving you the benefit of vast storage without overwhelming you with unnecessary information. Sparse models follow this same principle, ensuring scalability without exponential cost growth. That said, the efficiency of inference in sparse models does not fully eliminate training costs. Training mixture of expert systems is still resource-intensive, as the model must learn not only the parameters within each expert, but also the routing strategies that determine which experts to consult. During training, more experts are often activated than in inference to ensure broad exposure and learning, which inflates compute requirements compared to serving the model after deployment. This is analogous to building an orchestra. Rehearsals require every section to play extensively so they learn the score, even though not every instrument will dominate during the final performance. Training costs are a necessary investment to ensure experts specialize correctly, balance is maintained, and the routing system functions smoothly. While inference may be tractable and efficient, organizations must be prepared for significant upfront expense in the training phase. Hardware considerations further complicate the deployment of sparse architectures. Because experts are modular and may number in the hundreds, mixture of experts models are often distributed across many processors or even across entire server clusters. This parallelism ensures that whichever experts are needed can be quickly engaged, but it requires high bandwidth interconnects, synchronization protocols, and efficient communication. Without specialized infrastructure, routing tokens to experts across distributed hardware can create bottlenecks, undermining efficiency gains. Some hardware accelerators are now being designed with sparse workloads in mind, capable of skipping inactive weights and handling conditional computation. Still, the reliance on distributed systems introduces engineering complexity. Sparse architectures require careful orchestration of hardware and software, making them both an opportunity and a challenge for AI infrastructure. Research on routing strategies continues to evolve rapidly. Early approaches often relied on simple gating functions that selected the top one or two experts based on learned scores. While effective, these methods risked overusing certain experts while neglecting others. More advanced strategies now aim to balance efficiency, fairness, and specialization. Some use stochastic or probabilistic routing to diversify expert usage, while others incorporate auxiliary loss functions that penalize uneven distributions. There is also work on adaptive routing, where the model dynamically decides how many experts to activate depending on the complexity of the input. For example, a simple query might engage only one expert, while a complex task could involve several. These innovations highlight the importance of routing not just as a technical detail, but as the very heart of mixture of expert systems. The effectiveness of sparsity ultimately depends on how well routing directs information to the right specialists. Mixture of experts architectures are sometimes compared to ensemble models, but the two approaches differ in fundamental ways. Ensembles combine multiple independently trained models, often averaging or voting across their outputs to improve performance. This boosts accuracy but multiplies inference costs, since every model in the ensemble must be run for each input. Mixture of experts, by contrast, operates within a single integrated system. Experts are trained together as part of one unified model, and only a subset are activated per input. This makes them far more efficient than ensembles, offering the benefit of specialization without the proportional cost of running many models in parallel. The distinction is crucial. While ensembles represent brute force aggregation, mixture of experts represents smart allocation of internal resources. This difference in philosophy explains why sparsity has become central to scaling, whereas ensembles remain useful mostly in research or niche deployment scenarios. The potential of sparse architectures extends beyond text, particularly in multimodal systems. Experts can be designed to specialize not only in different tasks but in different modalities of input, such as text, images, or audio. For example, one expert might focus on visual reasoning, another on speech recognition, and another on narrative text. When a multimodal input arrives, the routing system can activate the relevant experts for each modality, allowing the system to process diverse data types seamlessly within the same framework. This specialization across modalities mirrors how human cognition relies on distinct brain regions for vision, hearing, and language, all coordinated into integrated perception. Sparse architectures therefore hold promise not only for scaling text models, but also for building truly general-purpose AI systems capable of reasoning across multiple sensory inputs efficiently. While sparsity reduces the amount of computation per input, it can also introduce latency trade-offs. Routing itself requires computation, as the system must evaluate which experts to select before processing begins. Additionally, when experts are distributed across hardware nodes, communication overhead can add delay. This means that although sparse models may use less raw compute per query, the added complexity of routing and communication can sometimes slow responses. Engineers must therefore weigh the gains of reduced compute against the potential for increased latency. Solutions include designing faster gating functions, co-locating experts to reduce communication costs, or batching inputs to amortize routing overhead. Balancing efficiency and responsiveness is an ongoing engineering challenge for sparse architectures. Sparsity also raises new security implications. Because sparse models rely on routing mechanisms, adversarial inputs could potentially exploit these mechanisms to misroute tokens or overwhelm certain experts. For instance, carefully crafted prompts might trigger unusual routing patterns that expose weaknesses in undertrained experts or bypass safety mechanisms. Quantization and pruning already introduce robustness concerns, and sparsity adds another layer of complexity. Ensuring that sparse models remain resilient requires rigorous testing, adversarial evaluation, and potentially redundant routing safeguards. At the same time, sparsity may enhance security in some contexts by distributing knowledge across multiple experts, reducing the risk of single points of failure. The interplay between sparsity and security remains an emerging area of study, but it is clear that routing mechanisms expand the attack surface in ways dense models do not. Open-source implementations of mixture of experts are making these techniques increasingly accessible. Frameworks like TensorFlow and PyTorch now include libraries and examples for building sparse models, and open-source communities frequently release checkpoints with MoE architectures. These implementations allow researchers and practitioners without frontier-scale budgets to experiment with sparsity, test routing strategies, and contribute improvements. The availability of open-source MoE models mirrors earlier democratization trends seen with quantization and LoRa, accelerating innovation by spreading tools beyond elite labs. As communities refine best practices for balancing load, handling training stability, and optimizing inference, sparse models are likely to become more standardized and easier to adopt across industries. Open collaboration will be essential for ensuring that sparsity matures from a frontier experiment into a mainstream practice. Evaluating sparse models presents unique challenges compared to dense ones. Accuracy alone is not sufficient. Efficiency metrics must also be considered. A sparse model might match or exceed dense baselines in benchmark scores while using far less compute per inference, making it superior in practice. However, evaluation must also account for utilization balance, interpretability, and robustness. For example, if only a handful of experts are ever used, the model may appear efficient but is effectively smaller than advertised. Proper evaluation requires measuring not just end performance, but also how well the architecture distributes load, scales with complexity, and adapts to new inputs. These additional dimensions complicate benchmarking, but are necessary to judge sparse systems fairly. They reflect the fact that sparsity introduces new axes of performance that traditional dense evaluation frameworks overlook. Energy efficiency gains are one of the strongest arguments for sparsity. Large, dense models consume massive amounts of electricity, both in training and in deployment, contributing to environmental concerns. Sparse models, by activating only subsets of parameters per input, reduce per-query energy consumption significantly. This makes them more sustainable for large-scale deployment, where billions of queries may be processed daily. Energy savings also translate into cost savings for organizations, aligning environmental responsibility with financial incentive. As sustainability becomes a pressing concern in the AI industry, sparsity offers a concrete path forward, making continued scaling possible without unsustainable energy growth. Sparse architectures represent not just a technical advantage but also a response to ethical and environmental imperatives. Industry trends show growing momentum toward sparse and mixture of experts designs. As dense models approach practical limits in size and cost, organizations increasingly look to sparsity as the next frontier of scaling. Frontier labs have already incorporated MoE techniques into their largest systems, and enterprises are experimenting with sparse architectures for efficiency in deployment. This momentum suggests that sparsity is not a niche experiment, but a mainstream direction for future development. Organizations view sparse architectures as a way to extend capacity without runaway costs, keeping pace with user demand for ever more capable models. The rise of sparsity marks a shift in scaling philosophy, from make everything bigger to make everything smarter about when and how it is used. Looking ahead, the future of expert models may involve adaptive, self-organizing systems that go beyond fixed routing and static expert roles. Research is already exploring dynamic experts that evolve over time, learning to specialize in new domains as they arise, or reorganizing to reflect changing workloads. This adaptivity could make sparse architectures not only efficient, but also resilient and flexible in ways dense models cannot match. Imagine a system where experts self-organize like teams in a company, forming new groups to tackle emerging challenges and disbanding when no longer needed. Such architectures would represent a profound shift toward AI systems that manage their own resources intelligently, scaling capacity fluidly in response to demand. This vision underscores why mixture of experts remains one of the most exciting frontiers in AI research. In conclusion, sparse and mixture of experts architectures represent a new chapter in scaling advanced AI. By decoupling capacity from per-inference cost, they make it possible to expand models to trillions of parameters without proportional increases in compute. Routing mechanisms allow specialized experts to activate selectively, creating efficiency, interpretability, and resilience. At the same time, sparsity introduces challenges in training stability, routing fairness, latency, and security. These trade-offs reflect the complexity of moving beyond dense systems, but the gains in scalability, energy efficiency, and versatility make sparse architectures an indispensable path forward. As research advances, expert models will likely grow more adaptive, multimodal, and self-organizing, shaping the trajectory of next-generation AI. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.